Hello and welcome back to Gaffy's Grinds. In this video, we're going to do an exam question walkthrough of the higher level titration question from the 2020 paper. So if you're watching this along in the Back to Basics titration series, then this may be one of the first higher level questions you've moved on to after you've practiced a good few of the ordinary level questions. And what you will notice typically is that the wording, the level of difficulty in reading the word problem here is a bit higher. And this is what separates, I suppose, the higher level from the ordinary level paper. All right, so what we're going to do is we are going to begin. I'm going to get you guys to very carefully have a read of this text. So hopefully you have your set of exam papers, and if you can find this question in there, it's the higher level 2020 question 1, and read along and just highlight anything that you think is important in that text. Okay, so hopefully you have had a read along. Just a quick note, things you might need is you will need a calculator, you'll need a periodic table, and you'll need something to write on, and hopefully you have your set of exam papers. All right, so what am I highlighting here? Well, first of all, I see it's the one about the washing soda crystals. That's the titration. So I'm expecting that at the end, we're going to have to find the percentage of water of crystallization. So we know that this formula here is Na2CO3. So the substance is sodium carbonate, but in washing soda, we have what we call hydrated crystals. So we have some water molecules attached to the Na2CO3 to make the crystals. And there's an X here. We don't know what number that is, but it will be a whole number. So there will be a certain amount of water molecules for every Na2CO3. The crystals are effloresce, which means they lose some water crystallization in dry air. So that straight away tells me if they lose water, then it's not suitable as a primary standard. So we shouldn't use this to make a standard solution. To determine the value of X, the formula Na2CO3 for a sample of washing soda, it says here that 3.46 grams of the crystals were dissolved in deionized water and made up to exactly 250 centimeters cubed. So in other words, there were 3.46 grams of this substance in 250 cm cubed. That might be important later. It says 25 centimeter cube volumes of this solution that we just made up were then pipetted into a conical flask. Okay, so that tells me the Na2CO3 here was in the conical. That might be important later on, so I'll just mark that. So they were pipetted into the conical and titrated with a previously standardized hydrochloric acid solution. So this is standardized, which means we know the concentration of the hydrochloric acid, and we titrated using a suitable indicator. All right, let's jump down to the questions now. It says identify a primary standard that could have been used to standardize the hydrochloric acid solution for this analysis. So here's the hydrochloric acid. It says it was previously standardized, so it must have been titrated against a primary standard solution. So your question, your answer here is to write down what solution could we have used. In other words, we need a solution that will react with HCl, and it has to be a primary standard, so something we can make a standard solution from. So it would have been in the titration previous to this. So hopefully you guys know this. There's really only one primary standard on the course. So do you know what it was? Pause the video and write down your answer now. Okay, so primary standard on this course, it's kind of a trick question because it's essentially this substance here. It's a base that will react with the acid Na2CO3, but this Na2CO3 is in some washing soda crystals. In the previous example or the previous titration, we used a purer version of this, so an unhydrated form. Okay, so what we used was anhydrous sodium carbonate. So this would have been done in the titration before this one, anhydrous sodium carbonate. So well done if you got that right. Let's go over check the marking scheme here. As you can see, yeah, anhydrous sodium carbonate, or you would have got it for the formula Na2CO3. All right, so it might have seemed like a trick question because this one was about Na2CO3, but this is the washing soda crystals. It's the same chemical, but this is the hydrated form. So we can't use this to standardize. We have to use the anhydrous version. Okay, so then it says B, describe how 250 centimeters cubed of washing soda was prepared, starting with 3.46 grams of washing soda measured out accurately on a weigh bowl. Okay, so this is where you have to really read the text to find out what they're looking for. This is the higher level, okay, which means we have to analyze really what exactly are they asking us to do. They're telling us already that we have this weighed out, so we don't need to talk about weighing that out. It's already given to us. on a weigh boat. So the little plastic boats that we use to weigh. And we have to describe how we made up the solution from that. So imagine I give you the tray of crystals and say, you take the rest. How do you make it up? And I'm talking in detail. We're looking for 12 marks here of how we make a standard solution from the weighed out sample. So again, you guys should be on this. This should be easy 12 marks. I always tell my students you can get 60% on this question at least without ever doing a calculation. So if you're someone who's struggling a little bit with the calculations, maybe you can't finish all of the calculations, maybe you can do the first bit, you can probably still get 40%, or sorry, 40 out of the 50 marks, 80% of this question from doing a little bit of the calculations and knowing the theory in this question. So focus on that, okay? If you're a higher level student, if you're really going for H1 or H2, you have to be able to do the calculations. But if you're not, don't get frustrated. The rest of the question is very accessible, okay? So I know my students are very good at making standard solutions and they should be very good at describing. We're looking for at least 4, 5, 6 bullet points, okay? But be on the safe side. If it's 12, it's probably 4 times 3. So 4 times 3, but that's 4 good scoring points. So it's always good to have 5 or 6 just in case they're not allowing marks for certain things in this year. All right, so pause the video and write out your description now. How do you prepare standard solution if I give you the sample weighed out? Okay, so you should only be playing if you've done this now. We're looking for the 12 marks. Let's go to the marking scheme. Here it says describe. Okay, so we want either this one or this one. So we begin with this. Let's just see how many different sections there are here. Look, there are 1, 2, 3, 4, 5, 6. So there's 6 different sections and you have to have at least 4 of them, okay? Now this little single line means you can have either the bit before or the bit after, and those are scoring, either one of those. If it's a double line like this on a marking scheme, that means that this is the first point, you have to have one of these. This is the second one, you have to have one of these. So that just means that you can't have this and get 3 and this and get 3, okay? Only one of these can get you the 3. You have to have one of them. Hopefully that makes sense. All right, so looking through your answer now and seeing did you get enough, pick up enough of the marks to get the 12, okay? The bold is the key bit of the information, okay? So stopper and invert is the key bit. Even if you didn't say several times, you can still get the marks here. If you just said stopper and invert, you will get the marks. All right, so going through that, let's mark your answer and hopefully we're all getting 12 there. What do I typically see most students do wrong when they're describing that? Just not including enough detail, forgetting little bits and pieces. You don't have to have every single word, but you have to have the key details, okay? So first of all, obviously you have to dissolve the crystals. We don't do this straight in the flask. You put it in a beaker first with the ionized water and you mix it to dissolve. Then you use a funnel to transfer the solution to the volumetric flask. Now you mightn't have said funnel. That's okay because there's still 5 other places you can get the marks, if you see what I mean. You have to get 4 times 3. So even if you didn't say funnel, that's okay. You can pick up enough marks in other places. But if you said use a funnel anywhere, then you're going to get that 3 marks, all right? Then after you've used the funnel, you're transferring it to the volumetric flask, transferring the contents. Add the rinsings, okay, into the volumetric flask. Top it up carefully using the ionized water. To the bottom of the meniscus is on the mark, the graduation mark, I might have said, and then stopper and invert. It actually doesn't say anything there about reading at eye level. So usually that's where another set of marks read at eye level, but it's not there in this particular occasion. Still, I'm hoping that we all had enough to get the 12 marks there. Good, let's go back to the text now. So that was, what, 17 marks so far. All right, and look at this, a really nice 12 marks here for the indicator and your color change and why we use this indicator. Okay, so pausing the video and answering the 3 parts about the indicator. So there's part 1, part 2, and part 3. Pause the video and answer them now. Okay, so the name of the indicator we would use here is methyl orange. Okay, so hopefully we said methyl orange. It's the only right answer here. And then justify your choice of indicator. Well, this is a strong acid, SA for strong acid, weak base titration, weak base. And in a strong acid, weak base titration, we use methyl orange. What is the color change at the indicator? It begins yellow in the base because it's mixed in the conical flask with the sodium carbonate, and at the end it goes red or pink. Let's go to the marking scheme so you can see that for yourself. Okay, methyl orange is the indicator. Why? It's a strong acid, weak base titration. That's why we use it. There are other possible answers there, but typically my students won't understand this yet because we haven't done pH and indicators in detail. You will by the end of the year, but not just yet by the time we're looking at these questions. Okay, this is what you understand for now, and the other bits you will add to your understanding later on. And then your color change is yellow or orange to red or pink. You have to have both of them and they have to be in the right order. Okay. Look here, if you put them in the wrong order, this year it was allowing you 3 for that. So if you said red to orange, they'll give, or red to yellow, they're actually giving you 3 marks instead of 6 for that. Sometimes they don't give you any though, so just being careful with that. So there's another 9 marks, or sorry, another 12 marks, lads. All right. So there is 12 and 12. That's half the marks for the indicator and making up the solution. So don't want you to get frustrated with the calculations, guys. It's really key. All right. The calculations are obviously important. I'm not saying don't bother with them, but I'm saying don't get frustrated. They can seem like the be all and end all, but remember that most of the question is actually not the calculation. And as well as that, of course, it's a guaranteed question. So even if you're able to get 70%, for some students, that's very good on a question. That might be better than you can do on another question. It's 70% if you know that bit of theory. And the theory is very similar most years. All right, so now we're straight into the calculation. Okay, part D. So I'm actually just going to rub this out for a second and make space here. We're going to do part D. And this is where it does get really wordy and really problem based. Okay. So let's just going to get you to pause the video and read this little bit here. Pause the video, do that now, and highlight anything that's important. Okay, so here I see 21 centimeters cubed, so that's the volume of 12 molar hydrochloric acid. Okay, so this is the volume used for the hydrochloric acid. We're required to completely neutralize the 25 centimeters cube portions of the washing soda. So the 25 centimeter cube portions were for the washing soda. Okay, and then it says find by calculation, and it's all in little bits. Now, your teacher may have showed you some formulas that you can use in a titration. And those are usually quite good for the ordinary level paper, but they really fall down here because when the question is asked in this way here, you really need to be able to use first principles methods to think your way through the question. The formulas are no good here. You will not be able to get the answers to questions like this. And this is the way they tend to ask them all the time now in the last few years. So this is why I focus so much on the first principles in this series, rather than trying to work with formulas that only work sometimes. And no, students don't really understand what they're doing, putting numbers in the formula. And then when it comes to a different type of question, they can't do it. Let's just though look at what it's asking us to do. It's giving us information. With that information, we have to figure something out. What is it asking us to do in part 1? Find by calculation, okay, the average number of moles of HCl used up in a titration. Some of you will be able to look at this now and say, okay, I can do this. I already know how to go from information about concentration, molarity, and find the number of moles. If you understand what you're about to do, let's pause the video and have a go at this now, please. All right, so what do we do if we're not quite sure? All right, and again, only here if you're not, if you're really having a clue, then I can help you, but you need to lose the crutch. I keep saying it. You have to try and take over yourself. But we want to find the average moles of HCl used in a titration. Well, the average moles per liter is 0.12 of HCl. 0.12 molar means 0.12 moles per liter. But that's if you have a full liter, moles in a liter. But we don't have a full liter in a titration. We have a lot less than that. We only have this amount. So the plan here is to go from moles per liter of HCl and find out how many moles are in a titration. So we want to get rid of the liters because we didn't use a full liter, and find out how many moles there are in the bit that we did use. Okay, so we have seen this loads of times before. We've done this hundreds of times. We've done it so many times earlier on in this series here. How do we work this out? Go from the concentration, the moles per liter, to the moles we used in the titration. We definitely want to get rid of liters here because we don't want liters in our answer. So let's think about that and let's have a go at this now. You pause the video and have a go. All right, first of all, if we're stuck here, okay, let me tell you what the answer is because sometimes that can help give you confidence. Let me just tell you. Okay, so the answer here to the first bit should be 0.00258 moles of HCl. So that's 0.00258. If you got that, well done. If not, maybe pause the video and have another go. See, can you work it out? All right, so writing down what we have here, we have a certain amount of moles per liter. That's this number here, 0.12. 0.12 molar means 0.12 moles of HCl in every 1 liter per liter. But we didn't have a full liter, so we want to cancel out the liters because we didn't have a full one. We had this volume. Now, again, we don't want to work in centimeters cubed and liters, so we need to work in the same unit. So what I'm going to do is I'm going to turn this into liters. At this stage, most of us know how to do this automatically. You move the decimal place 3 places to the left, and you should get 0.0215 liters. And of course, that means I can cancel out the liters there, and I'll get the number of moles of HCl in that volume, which was my titration volume. So that will give me get out your calculator, and let's have a go at this now. It's going to give me 0.12 times by 0.0215, and that equals 2.58 times 10 to the minus 3 moles, and that's of HCl. Okay, so well done if you got that right, and that's the same as what I told you earlier on, 0.00258. That's what I said the answer would be. That's the same thing, 2.58 times 10 to the minus 3. All right, so well done. That's part 1 done. We found out how many moles of HCl are used in each titration. Right, part 2, find out the number of moles of Na2CO3 neutralized in each titration. So that just means find out how many moles of Na2CO3 reacted with this many moles of HCl. So most of you will have an idea how to do that. Let's pause the video and have a go at that now. Okay, here's a clue for anybody. We know the moles of HCl. We know the equation tells us the molar ratios that they react in. So now let's use that to figure out the moles of Na2CO3. The answer you should be getting here is 0.00129 or 1.29 by 10 to the minus 3 moles of Na2CO3. So pause the video and see, can you get that now? Okay, so obviously here the plan is, well, we have moles of HCl and we want to go to moles of Na2CO3. So let's write down what we know. We know we've got 2.58 by 10 to the minus 3 moles HCl. Now, I don't want moles of HCl in my answer. I need that to be gone. And I want to be left with moles of Na2CO3. So I need this to cancel. So how can that cancel? It can cancel if I times by a conversion factor that has moles of HCl down here in the denominator. Then it can cancel like this. And then I can put moles of Na2CO3 in the numerator. Now, from my balanced equation, I can see that it's 2 HCl, 2 moles HCl for 1 mole Na2CO3. So stick that in my calculator now, the sum here, and I will get 1.29 by 10 to the minus 3. And that's moles of Na2CO3. Okay, all right, well done. If we got that, that's part 2 done. Okay, so we've got that one done, and we've got that one done. Now it says find the moles of Na2CO3 in 250 centimeters cubed of the washing soda. Okay. So this here was the moles in a per titration. Okay, moles per titration. But that was in a certain volume. It wasn't in a liter, was it? So it wasn't in a liter. It was in a different volume. So let's go down here. And we're going to go from moles per titration, so just moles, to moles per liter. Let me just think about this for a second. Yeah, so moles per titration, which is moles per, and it wasn't a full liter, was it? It was moles per 0.25. So sorry, 0.025. So it was 25 centimeters cubed. So moles per 0.025. And then we're timesing by a different amount. We want to find moles per 250 centimeters cubed, which is 0.25 liters. So notice the difference. This is 0.025 because this was the moles in 25 centimeters cubed. And we want to go to moles in 250 cm cubed, which is 0.25. Okay. So that's the plan. So what we're going to do is I'm going to get you to pause the video and see, can you work through this plan now? Let's pause the video and do that now. Well, of course, this was the volume. Sorry, this was the number of moles that was in 0.25 liters. So I'm going to do 1.29 by 10 to the minus 3, and that's moles of Na2CO3. And that was per, in this volume here, 25 centimeters cubed, 0.025 liters. And I want to know how many would be in 250 mils, which is 0.25 liters. Okay, so of course that can cancel out my liters, and of course that's going to give me a number of moles, which is what it asked me for. Find the moles in 250 centimeters cubed. Okay, so 1.29 by 10 to the minus 3 over 0.025, all that times by 0.25. And the answer I'm getting is 0.0129 moles of Na2CO3. All right, just checking, is that right? Yep, that looks good. So that's the next bit done. All right. And again, if you didn't get that far, you can still write this number down and try and do the next bit. Okay, so somewhere maybe you got lost here, and now hopefully that's helped you find it. You can still try the next bit. All right. Now it says find the mass of Na2CO3 in 250 cm cubed. So this is the moles, and now we got to find the mass. All right, so this is part 4. So this is moles. Sorry, I'll do this in red, the plan. All right, maybe actually, do you know what? Most of you can do this by yourself. Pause the video, plan this out, and then see, can you do the calculations? And the correct answer you're looking for here is 1.3674 grams of sodium carbonate in 250. 1.3674. If you got that, well done. If not, stay tuned. So we want to go from moles of Na2CO3, and we know that this was the amount of moles in 250. And we just want to go to the number of grams of Na2CO3. And of course, that's still going to be in 250 because we didn't change the volume. All right. So we begin by starting with our number of moles. It's 0.0129, and that's Na2CO3. And of course, we need this to cancel. We don't want that in our answer. Oh, sorry, I forgot to write down moles. Moles, Na2CO3. Cancel that out. How can I cancel this? I need to multiply by that in the numerator. Moles Na2CO3. And of course, that means I need grams of Na2CO3 in the denominator. Oh, sorry, in the numerator. So cancels in the denominator and leaves me with grams of Na2CO3 in the numerator. All right, so for 1 mole of Na2CO3, how many grams would that be? So pausing the video and working out the molar mass now. Okay, and the molar mass here is 106. So that's what we should have got when we got the mass of Na2CO3. And when we convert to grams, then that is going to be 1.3674 grams of Na2CO3, which was in the 250 ml solution we made up in the beginning, or the 0.25 liter. It's the same thing. All right, so that is the mass in the washing soda. Sorry, the mass of washing soda in the 250. Now it says find the mass of water of crystallization, and hence the number of moles of water in 3.46 grams of the crystals. Okay, interesting. Find the mass of the water of crystallization. Okay, so part 5. How can we figure out the mass of the water of crystallization? Okay, so most of you will have a way to figure this out. I'm going to get you to pause the video and think about how can I work out how much of the crystals was water. So pausing the video and writing this down now, figuring this out. Okay, I'm actually going to move this part 5 to over here. Okay. All right, so think about it. There was how many? There was 3.46 grams of crystals. 3.46 grams of crystals. How much could this have been, or what was this mass of crystals made up of? So we have a mass of crystals. What were the crystals made up of? Well, we know that some of them were the sodium carbonate, okay, because it was sodium carbonate crystals. All right, that's what was in them. So when we dissolved that much crystals, we got this much sodium carbonate. So this portion of, or this many grams of the crystals were sodium carbonate. So that means the rest must be water. So if we take the mass of the crystals and take away the mass of the sodium carbonate, Na2CO3, well then the remainder has to be the water. Okay, so pausing the video now, and from here and the numbers that we calculated before, you're going to work out the mass of the water. Do that now. Okay, so the crystals weighed 3.46 grams. That's what was weighed out. And they were dissolved into 250. When we did a titration, we calculated that there was 1.3674 grams of sodium carbonate. That was 1.3674 grams sodium carbonate. So when we subtract them and we get the remainder, the rest has to be water. Okay, and that gives us 2.0926 grams of water. Okay, now what was the second part? It says hence, so we've calculated the mass of the water, and it says hence the number of moles of water. Okay, so we've got grams of water. Now we're going to convert to moles of water. Pause the video and go from grams of water to moles of water. All right, so this should be pretty straightforward. We've got 2.0926 grams of H2O times by, we want grams of H2O on the bottom and moles of H2O on the top. And the next thing is if I have 1 mole, how many grams is that when my substance is water? Pause the video, work that out. Okay, you should have got 18, 1 each for the 2 hydrogens and 16 for the oxygen, so 18. So when we do this, we cancel out the grams of H2O and we're left with moles of H2O. And that's given me 0.116 moles of H2O. All right, there's one more bit here, so there's quite a lot of stuff going on here, but we're just following exactly what it says. It says, find the ratio of moles of water of crystallization to moles of Na2CO3 in the crystals. So what it's asking us to do, watch, it says find the ratio. So ratio, remember, is written like this, and it says moles of water to moles of Na2CO3 in the crystals, and hence the value of X to the nearest whole number. Okay, so we just found out that the moles of water here were here, 0.116 0.116, that was of water, is to, and a moles of sodium carbonate in 250. Where did we find that? Here it was down here, look. That's how much was the moles of sodium carbonate. So that's 0.0129. Now I'm just going to double check and make sure that was in 250. Yes, it was, because look, this is where we calculated it here. So we divided by 25 centimeters cubed, or 0.025, and then we found what it was in 0.25 liters. So it was this number, 0.0129. All right, so it's not quite clear yet what the simplest ratio is. It looks like it's about maybe 9 times bigger. Okay, so this one here looks about 9 times bigger than that one. But there's one way we can be sure, and that's to divide both by the smaller number. Divide by the smaller. Okay, so this one is the smaller number, the one on the right here. So I'm going to divide both of them by that number, 0.0129. And of course, that's over itself just gives us 1. And to divide it by itself gives us 1. But then what we're interested in is how many times does it divide into this one? Okay, so getting your calculator, and we're doing 0.116 divided by 0.0129, and the answer there is 8.99. 8.99, which we're going to round to 9. So 9 to 1, which means that there's 9 waters for every 1 Na2CO3. And that tells us that the value of X here is Na2CO3 dot, and there are 9 water molecules. So dot 9 H2O, because there's 9 times as much water as there is sodium carbonate. So here is 1 sodium carbonate, 9 waters. Okay, guys, so that is probably as tricky as any of the acid-base titration calculations are going to get. Hopefully you were able to stay with me. I actually like the way it's broken into little sections. Some people probably don't really, some people prefer maybe a little bit shorter calculation, but I mean, the fact that it's all in simple, like relatively simple steps, I don't think the wording in this one was that difficult. So maybe quite a nice one to start with. But yeah, that's the first higher level one that we're looking at, really. It's the first higher level one I'm recording. I will be doing some other ones. So I hope you found this useful. I hope it wasn't too bad, but just I want you to notice that you can get 29 out of the 50 marks just from theory down to here. Okay, so just from the theory, well over half the marks here are going for the theory, and then the first few bits here are relatively straightforward to get another 9 or 12 up towards 40 marks. Okay. All right, so that's it, guys. I'll see you in the next video. We'll look at another higher level titration.